Good afternoon, everyone. This is eighth interactive session or the problem-solving session for the NPTEL course Solid State Physics. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am a TA for this course. I am a research scholar from School of Physics, University of Hyderabad, and these sessions we have every Saturday 3 to 5, where we discuss mainly the numerical problems or other sort of problems related to that week's topic. And also, if you have any doubt related to the any part of the video lecture for this week, you can ask here and we can discuss. So with this, let's proceed for this session, and first let's have small recollection of what was the topic discussed last week. These are the recommended books. So last week we had discussed last week was about discussing and understanding the band theory of solids, that how in atoms, or like we have individual atoms with positive charge and negative charge around it, and when these atoms come close, then there is some change in their energy levels, and ultimately, when specifically we are talking about a solid material, electron and atoms are confined inside it, then the splitting or the modification in energy level leads to energy bands that we know. And based on these energy bands, we classify materials, electrically classify, saying that some are conductors, some are insulators, which have very high, whose resistivity is very high. Conductors have very small resistivity, and in between we say we have semiconductors, a type of materials for which conductivity or resistivity is in between conductors and insulators. So based on these energy bands, we say that for conductors, the energy bands, the valence band and conduction band, it may be almost overlapping. That's why the electrons from valence band need very small energy to go to conduction band, and that's how the conduction happens, electrical conduction happens. Whereas for insulator, the gap, energy gap or forbidden gap between conduction band and valence band is huge. That's why we need to apply large electric field or a lot of energy to make the electron go from valence band to conduction band and conduct. That's why the resistivity is high. And semiconductors, which have small gap, and that's why it's comparatively easier to make the electron go from valence band to conduction band. That's why resistivity is intermediate. So this is how from atoms and how they come together, that leads to change in energy levels and getting energy bands, and that helps us classify materials based on their conductivity or resistivity. This is what we had discussed. Then there are several models for this, and based on Kronig-Penney model, we had found out dispersion relation for solids, and these were the mainly, there was a lot of derivation last time. So this time, taking this electrical conductivity part of solid state, we will move on to semiconductors, because in present time semiconductor is like a very exponentially developing field in application, because all the chips, all the electronic devices that we use have semiconductor silicon chips in them, and that's why we need to understand what is so much significant about them, what is their importance. And that's why we are going to focus on semiconductors, try to understand what type of semiconductors are there, what is so important in them. Maybe we'll not go in detail as to understand the diodes and transistors, but just some understanding about semiconductors, and then some other also things. So we will see. Yeah, these we had seen how we get bands from this. Okay, so semiconductors, as we just now discussed, have electrical conductivity. As far as electrical conductivity is important, semiconductors' properties are said to be in between conductors and insulators. Semiconductors so are those type of materials for which the conduction band and valence band have very small energy gap. So again, the electrons in the valence band can easily go in the conduction band and lead to conduction in that material. Now, there are two types of semiconductors. Okay, one that we know and call as intrinsic semiconductor. The other is extrinsic semiconductor. And further we'll see in extrinsic also we have different classification. We'll see that here. So intrinsic semiconductor are just the semiconductors which are in their pure form, and when we add some outside atoms in it, the word for doing that is doping. That when we dope, that is like introducing some kind of impurity. So when we introduce some kind of impurity in the intrinsic semiconductor material, that leads to some change in their electrical behavior, and then we call it extrinsic semiconductor. So yeah, so how is a semiconductor? Like for example, in intrinsic semiconductor, we have examples like silicon and germanium. Is a group 14 element. So they have in their valence electrons, these things I think you must already be knowing, especially in the video of this week, but just a little revision. So intrinsic semiconductors, these elements have valence electron 4 with a group 14, and what happens is the atoms here, like for silicon atom, the valence inside electrons are there, but we know in reaction mostly the valence electrons participate. So silicon and several other such atoms, okay, they have 4 valence electrons. So they need to share and form covalent bonding, because when we had discussed bonding, we had seen that there is ionic bonding. There is some ion, they exchange positive negative ion and form a bond. And there are other bonds which what atom is basically trying to do is, if it has only one valency of electron, and if it gets that and it can become a neutral atom, I mean the noble element configuration, that leads to energy reduction in energy, that is it makes it stable. So that's why it wants to share, give or take electrons and make its electronic configuration as of the stable noble gas element configuration. But here it has only 4, so neither completely giving nor taking will be feasible. So what this kind of elements do is they share, like it is the same situation that is for carbon atoms, that forms covalent bonding with other carbon atoms. That means they share. This has 4, this is also 4 in valence electron, so they will share these two. So for this silicon atom there will be 8 electrons. Similarly for this it will share with the other one, so it will also have 8. So this way they form the bonding. This is how intrinsic semiconductor is. But even with this, the thing is that their energy gap is very small. So even with small uh, thermal excitation or electrical excitation, we can get conduction. But we can increase this if we do some addition of electrons or removal of electrons. That is when the doping concept comes, when we use, say for example, some trivalent atom or pentavalent atom. So what happens is, if we first take pentavalent, they have 5 electrons in their valence shell. That is 5 valence electrons. Example for this kind of pentavalent atom is phosphorus or arsenic. They have 5 valence electrons. So when we have a situation like this, that this is my silicon atom with 4 valence electron, now I introduce a phosphorus atom with very small amount. I'm not mixing like equal amount or something. It's like millions of silicon atom in between one atom of phosphorus. Then what happens is, there are all these silicon around it. So again they will bond with this. All sides are silicon atom. So they'll share. But it has 5 valence electrons. So even after sharing, it will have 1 extra electron. So earlier, when there was electrical conduction, we could not see any extra electron for moving around and participating in conduction. Only if we apply some thermal small energy, and if some electron will break loose, then the conduction may happen. But instead of that, if we just introduce a pentavalent atom, then there will be extra electron and the material will be ready for electrical conduction. But since this is not in its pure form, it has a foreign impurity introduced, it's called extrinsic semiconductor. And this is example when we introduce a pentavalent atom. When we introduce or dope trivalent atom, so what happens is, okay, this with the trivalent atom, that is in the valence electron, there are only 3 atoms. That means, and this is would be the example of p-type semiconductor. Okay, this when we use pentavalent atoms for doping, it leads to extrinsic semiconductor, which is called n-type semiconductor, because here the electron is more, means negative charge is more. When we use trivalent atom for doping, it gives us extrinsic semiconductor, which is a p-type semiconductor, because we'll see why. So in this case, if I introduce a trivalent atom like boron or aluminium, okay, these are group 13, group 3 atoms. They have valence electron 3. So see, if I have boron or aluminium with valence electron 3, and then all other are silicon around it, then these will share. But here it has nothing to share. These are all electrons. Okay. Yeah, that's fine. So this has nothing to share. So this is like a hole. And for semiconductors, usually we say that either the conductivity is happening because of the electrons or because of holes. So this is nothing, it's just the absence of electron. So how, like when we say electron is moving and conduction is happening, instead Like if electron is hopping from one place and going somewhere else, so where it left, there is deficiency in negative charge now. So we usually represent this hole as positive and we say this. So electron moved here and after that it will move here, means this negative charge is moving and it's leaving positive charge at back. So in a way, if we'll see, it will be like positive charge is moving from here to here. So it's just way of saying when there is excess of negative charge, it's n-type. When there is less number of negative charge and we have absence of negative charge, we call it hole. Okay, so these are two types of conductions we say, p-type, n-type semiconductors. One has n-type semiconductors have excess of electrons. Usually we should represent electron with this and hole with this gap. Here I just wanted to show that these are electrons. See, this is the problem. If I do this, there's some problem happens with my pen. So I just wanted to show these are just electron, but usually we use this open circle to represent holes. So this is, we say either there is excess of electron or there is excess of positive charge or hole. And this is what we get as p-type, n-type extrinsic semiconductor. And n-type semiconductor, just now we discussed, doped with pentavalent atoms, that is which have 5 electrons in their valence shell. Electrons are majority charge carriers here and holes are minority charge carriers. It gives out electrons, hence it is known as donor atom. Because pentavalent atom, when we dope using pentavalent atom, they are called donor atoms, and because they are giving electrons, they are donating electrons, so that's why these pentavalent atoms are called donor atoms. Example is bismuth, antimony, arsenic, all that group 15 elements. P-type semiconductor doped with trivalent atoms, that is atoms which have 3 valence electrons. Holes are majority charge carriers, electrons are minority charge carriers. It accepts electrons, hence known as acceptor atom. Example, aluminium, gallium, indium, and boron. Yeah, boron. Yeah, elements are used for doping. These were the basic of semiconductors. The next concept in the chronic penny model also we had seen that, so in this model of a solid matter, we have seen how we consider that we have atoms and their valence shell electrons are not restricted to the atoms. They are free to move around as long as they are inside the solid. So the potential we represent as like this, and from derivation further of this model, we had got dispersion relations. What another thing we had understood from this is concept of effective mass. Effective mass of a particle, or in this specific case, electron. So concept of effective mass comes when effective mass of electron is not its actual mass, because electron's actual mass, or rest mass also in quantum mechanics we call, is given by 9.1 times 10 to the power minus 31 kg. This is the actual mass. Effective mass is not actual mass until it is at a wave vector k is equal to 0, but rather a parameter used in solid state physics or condensed matter physics subject to describe how electron responds to forces with a crystal lattice. So this is like in a crystal lattice, means in a solid position of atoms is what we know as crystal lattice. So the electron moving around it, how it interacts with the potential force of these atoms, that leads to change in its mass. So we I mean, we explain it like this, that the electrons respond to the electrostatic forces of the atoms around it in the crystal lattice. It gives the behavior of free electron but with a modified mass. So if it's completely altogether free electron outside a solid material, then it will have the actual mass. But if it's moving around in a lattice, in a solid matter, in a kind of matter, then it will be, we can model its behavior like a free electron, but with it would have some modified mass. And that modification in mass, it's a consequence of electrons' interaction with periodic potential of materials atoms. This is the periodic potential of materials atoms and is determined by band structure, specifically the curvature of EK diagram. One of the results from this band theory is that movement of particle in periodic potential over long distance larger than lattice spacing can be very different from their motion in vacuum. Motion in vacuum gives us this mass, and when it's moving in a solid, then it's interacting with the crystal lattices and its mass is changed. Either it can become positive or negative also. For free electron, energy is h bar square k square by 2m, and the effective mass formula we know, it is h bar square divided by d2e by dk, double derivative of energy with respect to wave vector. And if for free electron, this is the value of energy. If we'll take double derivative, we'll get this, and when we substitute, we'll get back the actual mass. So for a completely actual free electron, rest mass, that's what I told, is equal to its actual mass. But when it's inside a lattice, then its mass changes. And how the mass changes? So when k is 0, wave vector is 0, the effective mass of electron approaches the mass m as the value of, the actual mass m, but as the value of k increases, it reaches maximum value, and then even further increase leads to effective mass being negative. So this is how, from energy k diagram, we get how the effective mass of electron changes in a lattice. Another concept that was discussed this week was of a very interesting phenomena that also helps further in understanding what kind of semiconductor we are using. These are usually used in graduation level physics lab experiment, where we want to find out what kind of material we are using. If the majority charge carrier, which we discuss in some materials, if it's extrinsic semiconductor, majority charge carrier will be electron. If it's p-type semiconductor, then majority charge carrier will be hole. So Hall effect, using Hall effect phenomena, this is the experiment with using which we can find out if in a material the majority charge carrier is electron or hole. The origin and how this comes into place, this also has been explained very well in this week's lecture. We'll just have a brief, just discuss this in brief. The Hall effect is a phenomenon in physics that occurs when magnetic field is applied perpendicular to the flow of current in a semiconductor or any kind of body we have. We have applied voltage, that means we are passing current. And then if we apply magnetic field, when the current is flowing through it, we apply magnetic field perpendicular, then we will get voltage across. This is not good diagram, maybe I should draw like this. Yeah. So if this is x, this is y, this is z direction, it means magnetic field is in z direction, current is flowing in y direction. Then there will be, if we'll connect a voltmeter from the back side to the front face, then we'll see a voltage difference will be generated across these two walls. That is what we know as Hall voltage. So here also it's a object. Here in this case, uh, let's see, if we call this X and oh shit, okay, let me draw it here. This is X, this is Y, this is Z. Okay, so here in this picture, the current is flowing in X direction. The magnetic field is applied in Z direction. So Hall voltage will be generated in Y direction, perpendicular to both. Why this happens is, we know that for any charged particle, the force it experiences if it is in presence of electric or magnetic field. We have this formula. So if that charged particle with the charge Q is in a electric field, is it in a region where there is electric field, then it will experience QE force on it. If there is no electric field, then there will be but there is only magnetic field, then it will experience a torque, because it's cross product of its velocity and the strength of magnetic field. So that means if velocity of that particle here, for example, whatever that kind of particle is, if let's say it's electron and it's flowing along X direction and magnetic field is along Z direction, then we know X cross Z will be minus Y. That means the Hall voltage. So what this means is the charged particle, if the charged particle is an electron and it's coming to X direction, but actually here it's I is in this direction, means electron's direction is opposite, right? If we say current is in this direction, means we consider electron is going in opposite direction, and this is the direction of positive charge or holes in this case. So if, for example, the positive charge, let's consider, is flowing in this direction, or the holes is flowing in X direction, that means the Hall voltage will be generated along Y direction. So that's why across these edges, if we measure the volt, if we connect voltmeter, we'll see a voltage drop. That is happening why? Because again, if electron is going or hole is going in this direction, it will experience force along Y direction. So it will go and it will instead of moving like this, because there is, we are applying current, means we have applied some voltage here. So instead of going the particle going in along X direction, it's experiencing force because of the presence of magnetic field and through this formula, and thus it's drifting along the wall depending on what kind of charge it has. If it has positive charge, it will go this direction. Okay, its force will be positive. If the charge is negative, that means this will be minus E. That means the force magnitude will be same, but direction will be opposite. So if it's positive charge, it will go and collect on plus Y side. If it's negative charge, it will go and collect on the minus Y, negative wall. I mean this opposite wall. So this is how, instead of going straight, they start collecting in this direction, and that's why if we'll connect a voltmeter, we'll see this positive charge, negative charge, they will give a voltage difference, and this is known as Hall effect or Hall, and this voltage is known as Hall voltage. So this is the main phenomena, and then using this, when we do a small derivation, we'll see the formula for Hall voltage depends on strength of magnetic field, the current, magnitude of current that is passing, N is the density of the majority charge, Q is the charge of that particle, if it's hole or if it's electron, and D is the thickness of that sample, that material. So what happens is, in experiment, what we do in lab, as I said, we can have it and then we can find out the either if all others are known, then one unknown we can find, right? If I am applying known strength of magnetic field and current also, I know how much I am applying, and the thickness of sample I know, then density of this I can find out, depending on taking, even if it's whole, the magnitude will change, positive to negative or negative to positive, but the value is 1.6 10 to the power minus 19 coulomb, right? So all these things I know, and VH I'll be measuring using a voltmeter, so I can find out the number density, electron density or hole density in my material. Similar way, if the value of from this, if I, and depending on what is the sign of the Hall voltage, if it's positive, that means my charge is positive. If it's depending on which direction I'm connecting, that is also one thing. But from this I can understand what is the majority charge carrier in my material. So it's widely used to, especially for semiconductors, to understand what kind of majority charge carrier is this. But otherwise also this Hall effect now has been developed into a lot of devices like sensors and various other very useful things in day-to-day life. So this was one thing. Another concept that was discussed was about Ford probes. Like usually when we have some material and we use a device to, we make some connection and we measure voltage and we measure current through emitter, then this is our connection, and we are using only 1 and 2, these two probes we use. So when we use something known as multimeter, it is a device which can measure both current and voltage, resistance, everything together. So it's like everything is inside it, and we connect one positive connection, one negative connection, and then we can see how much voltage is there when we are supplying this much current. But what happens, there are a lot of other aspects of material. It's the resistance is not only of the material, but the one that is the wire's resistance, because even the wire has its resistance, right? That's why we try to use in electrical connection the least resistive material, because otherwise that will also eat up a lot of energy. So in two probes, which we usually widely use for insulator material to find out its resistance, but we try to avoid using two probe method when we are trying to measure very sensitive way, but like the material which have very small magnitude of resistance, like metals or semiconductors, because there their value is so small that if the extra resistance from the wire through which we are supplying the current, if that is also getting added up, then we will not get the actual value of the material's resistivity. To avoid that, instead of these two probes, here we use 4 probes, that is 4 contacts. And it's not just the contact that is important, because otherwise it will be like earlier there were only 2 contacts, now there are 4 contacts, so resistance or inaccuracy should increase. But it's not just contact, it's the thing is here the current is passing through the emitter, it has some resistance which is getting added to the actual resistance that electron is facing in the sample only, and we are interested to identify the voltage along here itself. So instead what we do, we have 4 contacts like this, and in the outer contacts we are supplying current. So the current is flowing, let's say in this direction, and then separate contacts for voltage. Here we are supplying current, and in the inner one we are measuring the voltage drop. And now what happens, because voltmeter is in parallel, so if the voltmeter is something which is very high resistance material is used, so that no current flows through this. So current only we know goes through the least resistive path, that is this through this emitter. And because voltmeter is of very high resistance, so it doesn't flow from this, and we are able to get the correct, see the correct resistance or the correct voltage drop across this resistance, and then we can find out the resistance of the material. So that's why it's widely used for semiconductors or metals, where we want to find out, because their value of resistivity is very small. For insulators, the value is so high that it doesn't matter even if the circuits or the wires resistance is getting added. But for materials like semiconductors, metals, semi-metals, these things, it's very important that we remove the cause of errors or which can create inaccuracy. For that, we use separate contact for supplying current and separate contact for measuring the voltage instead of the same two probes. This is also a very important thing related to semiconductors. So these were the things, and then there were some derivations that you must have seen in the lecture videos. So based on this, I think now we can move on to doing some numerical problems. So the first question is, find an expression for density of states of free electrons. We find an expression for density of states of free electrons in 1D solid. Okay, so if you remember, we had discussed density of states last 2 weeks back. Yeah. So density of states is number of levels available for electrons or particles to occupy per unit energy. And density of state for 1D, we don't need to derive now. It's already been, we had discussed, and we had seen how density of states in different dimensions depend. Like for 1D, which is asked, density of state depends on energy as e to the power minus half. For 2D, it's proportional to e to the power 0. For 3D, it's proportional to e to the power half, and we had seen their graphs also. For 1D, the graph is like this, where E and density of state. For this, it's just constant. For 3D, it's like this. So in general, the formula, if we want to generalize, then density of state depends like it's e to the power n minus 2 divided by 2. If you remember this expression, you'll be able to find out. If it's 1D, then 1 minus 2 minus 1 by 2. If it's 2D, then 2 minus 2, 0. If it's 3D, then 3 minus 2, 1 by 2. That is this. So here for 1D, the correct answer will be, the dependence will be e to the power minus half. So e to the power minus half is this. Next question is, given that the effective mass of electron is 0.2 times its rest mass, calculate given that the effective mass of electron is 0.2 times its rest mass. Okay, so effective mass of electron, which we represent by m star, it's equal to 0.2 times its actual mass. Either we represent it using m naught or m like this, it's okay. Calculate its momentum when its energy is 0.02 electron volt. We have to find out its momentum, and its energy is given, which is 0.02 electron volt. Consider the electron at the bottom of the conduction band and the rest mass of electron. Yeah, that's what I told. Sometimes we call it actual mass, rest mass. Rest mass we usually represent with m naught, otherwise this subscript E is also used. Okay, we need to find out its momentum, and we already have been given the value of energy. So at the bottom of conduction band, electron is considered free. Okay, and for free electron, the energy expression is h bar square k square divided by 2m, and here the m star. Okay. Now also there is another relation, which is P is equal to h bar k. This is momentum and relation between wave vector. This is relation between energy and wave vector. That means we can write like this: P square by 2m star. From this, P square will be 2m star times E. That means P is equal to under root 2m star E. Right? Now if we substitute these values, E will be square root of 2 times. Now m star is 0.2 times me, and mass of electron me or m naught is 9.1 times 10 to the power minus 31, and that energy which is given 0.02 electron volt. Now electron volt we need to convert it into joules, because all this is an SI unit, and we know 1 electron volt is 1.6 times 10 to the power minus 19 joule. Okay, so this also 1.6 times 10 to the power minus 19 joule. This everything root we have to take. When we do the calculation, I'll use calculator. You should also know use calculator, because in exam also you will have digital calculator. So 2 times 0.2 times 1, 2 times 0.2 times 9.1 times 0.02 times 1.6 is 0.11648. Now all the powers if we take, then this will be 10 to the power minus 31 minus 19, and all to the power half, means root. If we solve this will be minus 31 minus 19 means minus 50. This when we will further solve, so this becomes so we had momentum is equal to 0.11648 multiplied by 10 to the power, this minus 31 minus 19 means minus 50, 10 to the power minus 50, and this whole square root we have to take. When we take square root of this, 0.11648 square root of 0.11648, that will be 0.34129, and square root of this will be 10 to the power minus 25. Momentum means kg meter per second, right? And answer here is, okay, it's after 1 decimal we need to shift this. That means this will become 3.41, and if I just keep it to 2 decimal digits, 10 to the power minus 26 kg meter per second. So the answer is 3.41 10 to the power minus 26 kg meter per second. This is the correct answer. Next question, the third question is now, okay, it's some expression given. The energy wave vector dispersion relation, that is the relation between energy and wave vector, is what we call dispersion relation. So energy wave vector dispersion relation for 1D crystal lattice with lattice constant A is given by this expression, where E naught, alpha and beta are all constants. Find the value of k, that is the wave vector, at which the velocity or the group velocity of electron is maximum, and also find out the value of that velocity. So the energy expression, the dispersion relation is given as E naught minus alpha minus 2 beta cos Ka. K is the wave vector, A is the lattice constant, and E naught, alpha, beta, A, all these are constants. We have to find out the group velocity of electron. Now group velocity, also written as Vg, is given by d omega by dk, angular frequency and wave vector. Okay. From this is one relation of a group velocity. Another relation that we will use is that E is energy, we know, is equal to h bar omega. If I take derivative with respect to omega, then I will get h bar, right? Now here, from here, if I try to find out the dW, it will be Vg times dk, and from here dW will be 1 over h bar dE. So if we equate these two expressions, because energy we already have, group velocity is d omega by dk. We have energy expression, so we want to correlate this formula with energy using this relation. So when we take derivative, we'll get this, that in terms of d omega, this is also in terms of d omega is this. So we can equate these two expressions. So after equating equation 1 and 2, we get Vg dk is equal to 1 over h bar dE over h bar dE. Okay, that means the group velocity, which earlier was in terms of d omega by dk, but we didn't have expression in terms of omega. So that's why we converted this in this expression. Vg is equal to 1 over h bar dE over dk. So it's something like 1 over h bar and dE by dk. So what we did, we knew group velocity is d omega by dk, and we changed this to this. This also you can do by just this, like E is h bar omega. That is what we did, but I just broke it down and told you in this way. Otherwise you can just substitute value of omega, which is E over h bar, and then it may create some confusion. So this was one way. So now h bar value we know, dE by dk. Now dE in terms of k we already have. If I take derivative with respect to k, I will get dE by dk. So let's take derivative of this expression. E is E naught minus alpha minus 2 beta cos Ka. dE by dk I need to find out. E naught is constant, that is given in the question. E naught, alpha, beta, k, these are constants. 2 is constant, we already know. So when we take derivative with respect to k, this dE naught by dk will be 0. Derivative of alpha with respect to k will be 0. If you guys have doubt in derivative, you can ask, I'll explain that also. But otherwise, I think if you already know, that's good. So I'm doing it directly. So here 2 beta is constant. Derivative of cos is minus sine Ka, and then derivative of Ka will be A. So this expression will become, this is 0, this is 0, this is a minus, this is a minus, so it will become plus 2 beta A sine Ka. This is dE by dk. So this group velocity expression, this will become, when we substitute dE by dk here, So group velocity will be 1 over h bar 2 beta a sine k a. Okay. Now we were asked the energy wave the group velocity when the maximum. Like the question was, we have to find out the value of k when the group velocity is of the electron is maximum. Now group velocity value is this. When will this group velocity value be maximum? For this to be maximum, the expression here should have the maximum. Since h bar 2 beta a, these all things are constants, so we cannot do anything about that. But sine expression, we know sine function, it goes from -1 to +1, everything in between. The least value it can have is -1, in between 0 also comes, but the maximum value it can have is 1. So for group velocity to be maximum, this sine has to be maximum, and the maximum value it can have is 1. So for group velocity to be maximum, sine Ka has to be maximum, and that maximum possible is 1. And when that happens is when this theta or this Ka is equal to n pi by a. n pi by 2, n pi by 2. And when this is the case, value of k will be, and Ka is n pi by 2. So k is n pi by 2a, and this is the value of k for which the group velocity will be maximum. This was the question, at which value of k group velocity will be maximum. So value of n pi by 2a, the group velocity will be maximum. We also need to find out the value of group velocity. So when we substitute value of k in this expression, let's do that. It's 2 beta a by h bar, 2 beta a by h bar, and sine n pi by, because here I am substituting sine k is n pi by 2a, and there was one a here, right? So what will this become? 2 beta a by h bar, and a gone, n pi by 2, the value will be 1. So the maximum velocity, the group velocity of electron will be 2 beta a by h bar, 2 beta by h bar, and k value will be this. So this is the correct answer. Next question is the energy, again it's on dispersion relation. Energy and wave vector dispersion relation for an electron in 1D crystal of lattice constant is given by this expression. E naught, alpha, beta are all constants. Find the difference in energy, that is energy gap between the top and bottom of energy band. So we have energy band, we have to find out the difference in energy between the top band, top and bottom. Basically we need to find out this energy band gap. For this, again, so E is this, and this energy at the top of the band it is maximum, and at the bottom of the band energy value is minimum. We know, like if this also here also not in the band gap, only if within this band also, if we see, we know as we go up we are referring to increase in energy. So the bottom has less energy, the top has more energy. So the energy expression value will be maximum. The top of the energy band will have more energy, and bottom of the energy band will have less energy. That means this expression will represent maximum when these E naught is constant, alpha is constant. Again, only thing that is variable is cos expression, and for this Ek to be maximum, the energy expression that we have been given, it can become maximum when this value becomes minimum, because it's getting subtracted, right? So if this becomes minimum, then this Ek will be maximum. I hope that makes sense. So when cos will be minimum, Ek will be maximum, and then it will represent the top energy level of the energy band. So for cos Ka, we know like sine, cos function also goes from -1 to 1 in between 0, and for cos 0 it's 1, for 90 it's 0, for cos pi it's -1. And we just now said that for the energy to be maximum here, cos has to be minimum, and the minimum value cos can take is -1. So if cos Ka is -1, then we will get the maximum energy, which will be the energy of the top energy band. And when we will substitute cos Ka minimum value -1, the expression will become, if there is any doubt in this step, you can ask. I think it's straightforward. For 2 beta, and cos minimum value it can take is -1. So this will be E0 minus alpha, and this will become plus 2 beta. So this is the energy of the top of the energy band, because this is the maximum energy possible. Now we have to see the energy for the bottom of the energy band, because bottom will have less energy and least energy in this case, and this expression will be minimum when we subtract something big. Something big, all these are constants, only this can vary, and the maximum value cos function can have is +1. That means when cos is +1, we will have the minimum value of this E expression. So the bottom of the energy band, it will be minimum value, and that will happen when E0 minus alpha minus 2 beta, and the cos will take the maximum value, which is +1. Then this expression will be E0 minus alpha minus 2 beta. So this is the energy of the top of the energy band and the bottom of the energy band. Now we have to find out the difference in the energy of top and bottom of the band. For that, we will subtract E top minus energy of bottom level of energy band. E top expression was E0 minus alpha plus 2 beta. E0 minus alpha plus 2 beta minus, this is energy of top energy level, and energy of bottom level is E0 minus alpha minus 2 beta. E0 minus alpha minus 2 beta. When we subtract E0 minus alpha plus 2 beta minus E0 plus alpha plus 2 beta. E0 will subtract plus alpha minus alpha, we will be left with 2 beta plus 2 beta. That means 4 times beta. So the energy difference here is 4 beta. So option D is the correct answer. Next question. This is again on dispersion relation. For electron in 1D crystal of lattice constant, energy is given by the same expression, E0 minus alpha minus 2 beta cos Ka. And these E0, alpha, beta are constants. Find the effective mass of electron at the bottom and at the top of the energy gap. So last time we had just found out the value of energy. Now we need to find out the effective mass of electron when it is at the bottom and when it is at the top of the energy gap. So like if this is the energy gap, then we have to find out what is the effective mass of electron when it is at the bottom of energy gap here, and when it is at the top of the energy gap, that is here. So these two values we need to find out. Now we know effective mass of electron which we represent by m star. It is given by the expression h bar square divided by d2e by dk square, right? In denominator we have double derivative of energy of this expression. So we need to find out double derivative of this. Now first derivative of dE with respect to k, E naught is a constant, so it will be 0, minus alpha is a constant, this will also be 0, 2 beta constant, so derivative of cos is minus sine Ka, and derivative of Ka will be A, because A is a constant. So here what we will get is 2 beta times A times sine Ka. This is first derivative. We need second derivative. So we will take derivative again. This is basically like this. First we took first derivative and we are taking second derivative of it. That is, we write d2e by dk square. So when we take derivative again, now 2 beta A all are constants, so just keep them apart. Then derivative of sine Ka means cos Ka. This, remember, the derivative of cos is minus sine and derivative of sine is plus cos, and derivative of Ka will be A. So this value we found. Now we have to find out when the effective mass of electron when it is at the bottom of energy gap and top of energy gap. So when it is at the bottom of energy gap, we just now had seen in this question, bottom of energy gap means the energy is less, top means energy is higher, of course. Same concept here we'll use, that when the electron is at the bottom of the energy gap or at the bottom energy level, that means the value of energy will be less, and the energy will be less when cos will be maximum, right? Because it's getting subtracted here. Please pay attention. So that's why if it is maximum, E will be minimum. So for the bottom energy level, or for the bottom of the energy gap, E will be minimum, and E will be minimum only when cos Ka will be maximum, and the maximum value it can have is plus 1. In that case, so for bottom, so what we mean is, first I took out this double derivative, I can substitute. So effective mass of electron will be h bar square divided by, I have taken double derivative and the expression is this 2 beta A. We have one more A, so it will be 2 beta A square cos Ka. 2 beta A square cos Ka. This expression we found for this material. This is the effective mass of electron. But now we have to find out the effective mass of electron when it is at the top of energy gap and when it is at the bottom of the energy gap at these positions. So at the bottom of energy gap, for the energy to be minimum, cos A should be maximum, that is it should be plus 1. So cos A should be plus 1 at the bottom of energy band. So for first situation, that is at the bottom of energy band, effective mass of electron h bar square divided by 2 beta A square, and I will substitute instead of cos A plus 1. So we will get this expression. Second situation, we have to find out effective mass of electron when it is at the top of energy gap. There the energy will be maximum. Energy will be maximum, and for energy to be maximum, this should be minimum, and cos minimum value it can give is -1. Okay, so for when the electron is in the top of the energy band, energy will be maximum. That means cos A has to be minimum, and the minimum value it can take is -1. So when the electron is here, cos Ka will be -1. So effective mass of electron will become h bar square divided by 2 beta A square, and instead of cos A I have to write -1. So basically this will be minus h bar square divided by 2 beta A square. So this is how, depending on where the electron is, its effective mass changes. See, it even becomes positive, negative, depending on which energy level it is. So these are the expressions. So A is the correct answer. Okay, next question, question number 6. The energy of electron near the valence band edge of crystal. So this is valence band. If let's say this is conduction band, then at the valence band edge, energy of electron is given by minus AK square, where A is some constant whose value is given. An electron with wave vector this is removed from the completely filled valence band. One electron is removed from here whose wave vector is 10 to the power 10 per meter. Completely filled valence band, this electron is removed. Find the effective mass. You have to find effective mass and momentum of hole. So when electron is removed from this place, what is left? We had discussed when we were discussing about extrinsic semiconductor, specifically when we were discussing p-type semiconductor. Then when there is vacancy or absence of electron, that place is called hole. So here we have removed electron, that means what we have remained with is hole, and we have to find out momentum of this hole. Okay, so one another thing, we say absence of electron. So all the magnitudes are same, the signs are opposite. Mass for electron is 9.1 10 to the power minus 31 kg. For hole, it will be the same. Charge will be opposite because its absence of electron means this is positive charge. Wave vector for electron is this, that means wave vector for hole will be the same magnitude but sign will be reversed. So this is the relation between hole and electron that we'll use to find out the momentum of hole and effective mass. So effective mass of hole formula we have not derived, but if we find out effective mass of electron, we can just change the sign and then we'll get the effective mass of hole. So the formula for effective mass of electron is h bar square divided by d2e by dk square, that is double derivative of energy expression. Here E is minus ak square. If I take first derivative with respect to k, minus a is constant, derivative of k square means 2k. I have to take one more derivative, so d2e by dk square. Now minus 2a is constant, derivative of k with respect to k will be 1. So this will be the final expression. So effective mass of electron h bar square divided by, this is minus 2a in denominator. Now this is the effective mass of electron. I told you the hole will have everything same, only the signs will be reversed. So effective mass for hole will be, here it is, if I write like this, h bar square divided by 2a. So for hole it will be h bar square divided by 2a. This was for effective mass of electron. Effective mass of hole will be h bar square divided by 2a. And in magnitude we have to find out, we know h, we know a is given. So h is given, so we need to find h bar is actually h over 2 pi. So h bar square means h square divided by 4 pi square, also multiplied by 2 multiplied by a. When we substitute the values here, we'll get effective mass of hole will be h, value of h is, we have to take square of this, 6.62 times 10 to the power minus 34, 6.62 times 10 to the power minus 34, square of this, and then we have 4 times pi square, 4 times pi square, and 2 times a. What is the value of a? 10 to the power minus 39. 10 to the power minus 39. When we calculate this, let's see what we get. So in the numerator, 6.62. 6.62 multiplied by 6.62, that will be 43.8244, and these powers, that is 10 to the power minus 68. In denominator, 4 times pi square times 2. That will be 78.9568. This 4 times pi square times 2, and 10 to the power minus 39. So this will be 43.8244 divided by 78.9568. This will be 0.5550 times, and this will be 10 to the power minus 68, and this, when this expression, this power will come in the numerator, it will be plus 39. So minus 68 plus 39 minus 29. 5550, 10 to the power minus 29. And this effective mass, this is in kg, and if I shift the decimal, it will be 5.55, 10 to the power minus 30 kg. So this is the effective mass of hole. If I put negative sign here, then it will be effective mass of electron. So the correct answer is this first, because all other, this is the effective mass of electron. This is not what we are getting this. Also, we need to find out the momentum of this hole. How we will do this? So wave vector we are given for electron. Wave vector of electron is this, 10 to the power 10, 10 to the power 10 I cap per meter. So wave vector for electron, for hole, it will be everything same, sign revert. I, it will become I, instead of I cap, it will be minus I cap basically, and meter inverse. And momentum is, what is the relation between momentum and wave vector? It's like this, right? And h bar again, h over 2 pi, and k is this, minus 10. So with this, we'll have a direction. So the value will be 6.62 times 10 to the power minus 34 multiplied by minus 10 divided by 2 times 3.14. When we'll calculate this, 6.62 times 10 divided by 2 divided by 5, it will be 10.5361, and power 10 to the power minus 34. Oh, I'm very sorry. This minus 10 to the power 10. It's k vector. K way vector. 10 to the power minus 10 it is. I'm sorry. I made a mistake. So this will be 6.62 divided by 3. 2 divided by... This will be 1.0536, and 10 to the power minus 30 minus sign, because this is minus, and the minus 34 plus 10 means 10 to the power minus 24 joule second per meter. This will be the wave vector for hole. So minus 1.05 10 to the power minus 24. This is the momentum for hole. A is the correct option here. And next question, compute the ratio between the kinetic energy of a free electron in 2D square lattice. The first situation is kx, ky is pi by a. Second is kx is 0, ky is pi by a. Okay, so for this question, we know for a free electron or for electron inside a Brillouin zone, energy for 1D, energy is given by h bar square k square by 2m. In 2D, we will have kx and ky. That time, the energy will be written as h bar square divided by 2m, and instead of k square, it will be kx square plus ky square. For 2D, this will be the situation. We have to find out the kinetic energy of free electron in 2D square lattice when kx is equal to ky is equal to pi by a. That means this energy expression will become h bar square divided by 2m. Kx, ky is pi by a. So pi square by a square plus pi square by a square, same. So this will be 2 times, right? 2 pi square h bar square divided by 2m a square. So this will be on pi square h bar square divided by m a square. Now the next part, B, when kx is 0 and ky is pi by a. In this case, the energy will be h bar square divided by 2m, and kx is 0, ky is pi by a square. So this will be h bar square pi square divided by 2m a square. We have to find out ratio of kinetic energy of free electron for A case and for B case. We have to find out this ratio. Now for E case, the energy was pi square h bar square divided by m a square, and for B case, the energy expression was h bar square pi square 2m a square, or 2m a square. So when we take these division, then pi square cancel, h bar square cancelled, m cancel, a square cancel, we'll be left with this 2. And this is like 1 over 1 by 2, right? This is 1 by 2. There is nothing here, 1. This means 1 divided by 1 by 2. That means 1 multiplied by reciprocal of this 2. That means the ratio is 2:1, or the ratio is 2. So A is the correct answer. Next question. Using the Kronig-Penney model, and the expression is given, calculate the energy of electron for the lowest energy band at k is equal to 0. So we have to find out the energy of electron for lowest energy band when wave vector is equal to 0. When using Kronig-Penney equation, which is this equation, E sine alpha A divided by alpha A plus cos alpha A is equal to cos Ka. A is the interatomic separation and alpha is equal to 2me over h bar square whole root. This is the equation. Now we can rearrange this and then we can write it like this. If I take cos alpha to because we have to find out the energy when k is 0. So when we put k is equal to 0 in this equation will become p sine alpha A divided by alpha A plus cos alpha A is equal to 0 because, sorry, it will become 1 because cos 0 degree is 1. So this will be 1. Now I'll rearrange this equation and write like p divided by alpha A, and I will send this to right side, then it will be 1 minus cos alpha A, and then I will take this to right side, then it will come into a denominator sine alpha A. Okay, now I'll simplify this expression because alpha A is p is very small than A, and that means alpha A is also very small than 1 is very small value. So I can use trigonometry and make it right. So the expression that I'm left with is this 1 minus cos alpha A divided by sine alpha A. Now I have two trigonometric equations. One is sine 2 theta is 2 sine theta cos theta. Using this, I can change this to this sine alpha A. I can change to sine 2 sine alpha A by 2 cos alpha A by 2 because this angle is double of this angle. Sine 2 theta is equal to 2 sine theta, cos theta is one identity. Using this, I can expand it like this. And I have one more identity, which says cos 2 theta is 1 minus 2 sine square theta. Using that, I'll replace this. So this will become, so cos alpha A will become 1 minus 2 sine square alpha A by 2. So that I can simplify this. When I will do this, this will be 1 minus 1 minus 2 sine square alpha A by 2, and in denominator I have this, I've changed to this. So 2 sine alpha A by 2 cos alpha A by 2. When I open these brackets, it will be 1 minus 1, and this will become plus 2 sine square alpha A by 2, and in denominator 2 times sine alpha A by 2 cos alpha A by 2. 1 minus 1 0, and this, so here we'll have only this. 2 cancel, sine alpha cancel, we'll be left with 1 sine alpha, and in denominator cos alpha A by 2. Sine over cos is tan alpha A by 2, and because we assume that p is very small, that means alpha A also has to be very small, and when that happens, so tan theta in expression, when this angle tan of whatever angle we are taking, if that value is very small, then we can simply write tan alpha A by 2 is equal to alpha A by 2. So this is the value of p by alpha A, right? This is the value of p by alpha A. That means the value of p will be, we have to equate this and this. This directly tan some angle we can directly write at this, because the alpha A by 2 is very small. Okay, then only this approximation is correct. So p by alpha A is equal to alpha a by 2, alpha a by 2, that means P will be equal to a square alpha square divided by 2, and alpha is this. So when I put the value of alpha is given under root 2me over h bar square. So alpha square will be 2me over h bar square. So when I substitute here, in place of alpha square, then it will be 2me over h bar square. We had to find out what? We had to find out energy of electron. That means we need to find out E. These are all our small referred. So energy expression in terms of P, it will become 2h bar square times P, and in division we'll have 2ma square, and then this will go and we'll be left with h bar square P by ma square. So the correct answer is, okay, so interesting, they have not kept the answer in h bar, but they have kept in h. So we need to do conversion. Not conversion, I mean h bar is h over 2 pi, we know. So this expression will become h square 4 pi square ma square and p. So h square p 4 pi square ma square. Option A is correct. Next question. Estimate the band gap of an insulator if it absorbs electromagnetic radiation of wavelength below 3000 angstrom. So it's an insulator and it absorbs wavelength below 3000 angstrom. It's all the wavelength less than 3000 angstrom it absorbs. We know something, energy is given by this, or h nu. Energy is directly proportional to frequency but inversely proportional to the wavelength. That means if we are saying, like we know for insulator, electron takes some, if you supply some energy, it goes from valence band to, it jumps to conduction band. So it requires some energy. If the energy gap, let's say, if the energy gap is 7 electron volt and I am supplying 1 electron volt, 2 electron volt, 5 electron volt, 6 electron volt, 6.7, 6.9 electron volt, still it will not, band gap is large. So if I am applying up to 6.9 electron volt, the electron will not absorb and go to the conduction band. This is the meaning here, that it's absorbing, because it will absorb that energy and go to conduction band. So it needs minimum 7 electron volt. I'm just giving an example that it needs this particular energy, minimum this much energy. If I'm giving it 8 electron volt, it will take that because it's more than the energy gap. So that means an insulator needs particular amount of energy, the minimum energy, to overcome the gap. That means if minimum energy is some value, that means it will take any energy value above that and absorb. Also means that it will take all the values smaller than the wavelength, because this is inversely proportional. So if it will take more than that energy value and absorb, it means it will take less than that some particular wavelength corresponding to that energy that we can find out, corresponding to that energy, that will be the maximum it will absorb, and anything more than that it will not absorb, because it will mean it's any wavelength more than this particular wavelength will correspond to the energy less than this. I hope I could make this clear, because here we have been given wavelength. So to understand why the electron will absorb the wavelength below this and not above this. To make that statement clear, I am trying to make you understand that usually when we talk about electrons will absorb and go from valence band to conduction band, the energy should be equal or more than the forbidden gap. So it can take any energy more than this forbidden gap value. So this is the minimum energy it requires to absorb. Correspondingly, the wavelength will be some lambda naught, and because they are inversely proportional, so if I say it can take any value more than E naught, that means it can take any wavelength less than this, because any value more than this will be equal to energy less than this. I hope this is clear. So here we have been given that estimate the band gap of insulator if it absorbs the radiation of wavelength below 3000 angstrom, means that 3000 angstrom will correspond to some energy value which will be the minimum energy above which it will absorb, and this 3000 angstrom is the maximum wavelength below which it will absorb. So these energy and wavelength are inversely proportional. I just wanted to make that clear. Okay, so now we have to calculate the energy gap. Now, if the wavelength is 3000 angstrom, then we can calculate energy, because energy told is hc over lambda. H is 6.62 times 10 to the power minus 34 given, and C is the magnitude of light, speed of light, 3 times 10 to the power 8 meter per second, and lambda is given 3000 angstrom. Angstrom will change to meter. 1 angstrom is 10 to the power minus 10 meter. So 3000 angstrom multiplied by 10 to the power minus 10, this will be in meters. So when we will do this calculation, we will get 6.62 times 3 divided by 3000. This will be 6.62 times 10 to the power minus 3, and then we have 10 to the power minus 34, 10 to the power 8 and 10 to the power minus 10. That means exponents will be 10 to the power minus 34 plus 8 plus 10. Okay, let's do this. So minus 3 plus 10 minus 34 plus 8. So it will be 10 to the power minus 19. So this will be 6.62 10 to the power minus 19 joule, because everything was in SI unit. So energy value that I am getting, it will be in joule. And our answers are in electron volt, so we need to convert it into electron volt. Now we know 1 electron volt is 1.6 times 10 to the power minus 19 joule. Okay, so to convert joule into electron, I will divide this 6.62 times 10 to the power minus 19 joule divided by 1.6 into 10 to the power minus 19, and I will get the answer. So 1 joule will be 1 over 1.6 times 10 to the power minus 19, right? So to convert it into electron volt, we'll get this will be 6.62 divided by 1.6, be 4.1375, and this will be cancelled. So this will be 4.1375 electron volt. Okay, I need to restrict it up to 2 decimal digits. It means 4 point, this will make it 8, this will make it 4.14 electron volt. B is the correct answer. One more question. This is the question based on Hall voltage. The question is, a copper strip of thickness 0.01 centimeter 0 is in a magnetic field of 0.5 Tesla. Current of 3 ampere flows in that strip. Given that the charge carrier density in copper is 8.5 times 10 to the power 28, this is 10 to the power 28, this is m to the power minus 3, and the charge of electron is 1.6 times 10 to the power minus 19 coulomb. This is 10 to the power minus 19 coulomb. Calculate the Hall voltage. So direct formula we know that VH is equal to, it's seen right, it was current multiplied by magnetic field divided by charge and the charge density and thickness of sample. Substituting these values, current 3 ampere, magnetic field 0.5 Tesla, charge of current 1.6 times 10 to the power minus 19 coulomb, charge density, carrier density 8.5 10 to the power 28 per meter cube, and the thickness of sample. So everything is in SI unit. So we should better convert this in SI unit also. It's in centimeter. In meter it will be, because 1 meter is 100 centimeter. So 1 centimeter is 10 to the power minus 2 meter. 0.01 10 to the power minus, no wait, yeah correct, 0.01 10 to the meter. So this B, which is 0.01 times 10 to the power minus 2. Okay, when we calculate all this, 3 times 0.5 is 1.5 in the numerator, and in denominator 1.6 times 8.5 times 0.01, it will be 0.136, and now we have to take care of these powers. So 10 to the power minus 19 plus 28 minus 2. Okay, so this will be, if I calculate this, 1.5 divided by 0.136. This will be 11.0294, and the powers, so minus 19 plus 28 minus 2. Sorry. Minus 19 plus 28 minus 2. That is 10 to the power 7. When it will come into numerator, it will become 10 to the power minus 7 volts. Because it's voltage, everything is in volts, and this is the answer. If we want to write in some like the microvolt, then we can write it like this. If I shift the decimal point, it will be 1.10294, and this will be 10 to the power minus 6 volts. We can also say this is 1.1 microvolt. The correct answer will be 1.1 microvolt, or we can just leave it like this. If there is some options, then we can finalize our answer accordingly. So this was one question. So these were the things, concepts based on basics of semiconductors. We understood what is p-type semiconductor, n-type semiconductor, intrinsic, extrinsic, then effective mass of electron was one concept that was discussed this week. Then Hall voltage, 4 probes of finding out resistivity for sensitive in the sense which have very small resistivity. So for those metals or semiconductors, we use 4 probe technique. So these were the major concepts discussed. So we revised them and also did these problems based on this. And I hope you guys understood all this, and question you can please ask. If not, then we can end this session. I'll stop the recording.